So we're talking about n-linear functions, also called multilinear function of an n by n matrix. Let's say that A is a matrix defined over a commutative ring K. For the sake of simplicity, we can say that this ring is just the field of real numbers. So it's an n by n matrix defined over a commutative ring K. Then A would look like so. So that we have the first row, which starts with A11, A12, and so on till A1n. And then the second row is A21, A22, so on until we get to the final row, that with the last element of the matrix being ANN. So it's a square matrix. So I just want you to keep in mind that this is a generic representation of an n by n matrix that I'll be using in this. We can also say that each row of A would be denoted by letter alpha, so that alpha 1 is the first row, alpha 2 second row, and so on till alpha n. Then a function d of A, which is a multilinear function of A, could also be described as a function of all of these rows as d of alpha 1, alpha 2, and so on until alpha n. N-linear means that if we take any ith row, alpha I, and we make the function a linear combination of this ith row, while we keep all the remaining rows fixed, then d of A can be represented as a linear combination, as described here, where C is a scalar multiple, so we multiply the ith row with C, and then we add another row to this ith row, which we will denote by alpha I prime. And keeping in mind that the remaining rows are fixed, then D can be split into two parts, like so. So I would say that at a first look that this definition might look a bit confusing. So I think it might help to explain this with the help of an example. So from the same book, Hoffman and Kunze, there is a problem at the end of the section from which I've picked up two examples. So in the first example, both of which are applied to 3 by 3 matrices A, d of A is simply the sum of the diagonals. So that is also the trace function. So that will be the first example we'll explore and find out whether that function d of A is n-linear or 3-linear or not. And in the second example, d is simply the product of A11, A22, and A33. And we'll find out whether this other function is n-linear or 3-linear or not. So if we take A as a generic 3 by 3 matrix, as shown here, and then the function d of A becomes a sum of the diagonal terms, A11 plus A22 plus A33. So that would be the first example. To look at this in further detail, I'll use a numerical example. I'm going to create a simple matrix A. Each row of it is just one number repeated, alpha 1, alpha 2, alpha 3. And we can also say that the second row of A can be represented as a combination of two rows, one of which is simply 2, 2, 2, which will be alpha 2, added to which is alpha 2 prime, which is 4, 5, 6. So that now the matrix A looks like first row 1, 1, 1, second row being 6, 7, 8, and the third row again being 3, 3, 3. In other words, the second row is a linear combination of alpha 2, which is 2, 2, 2, and alpha 2 prime, which is 4, 5, 6. The definition of n-linearity simply implies that the function d, when applied to the whole matrix which is the sum of the second row while the first and third rows are kept fixed should be equal to the sum of the function applied separately to each of the component matrices. Here I would just like to re-emphasize one point, that the matrix on the left side of the equation is not actually literally the sum of both matrices in the traditional sense, and that the first row is not the sum of the first rows. You can see that the first row of the final matrix is 1, 1, 1, and the component matrices both have 1, 1, 1 in the first row. So if you were to sum them up, you would get a 2, 2, 2. But n-linearity means that the rows, all rows except for one, have to be fixed. So we are not going to sum up the first and the third row in the matrix on the left side, but only the second row. I'm going to simply check whether the trace of the matrix on the left side equals a trace on the right side, and if it does, then this function, which is the trace, is an n-linear function. So on the left side we sum up the diagonals and we get 11, whereas on the right side we obtain the trace of each component matrix. So for the first matrix we get 6, add to that we have 9, and the sum is 15, which is not the same on both sides. Therefore the trace is not an n-linear function. In the second example, d of a is the product of the diagonals, so a11 times a22 times a33. In this simple example, I'll show quickly that this indeed is a three-linear and linear function. So on the left side, as usual, we have a matrix, the second row of which can be split into two rows, and the product of the diagonal elements on both sides will match in this example. So on the left side, the product is 5 times 3 times 1 equals 15. On the right side, when d is applied to the first matrix, it is 3 times 2 times 1, 6, add to which 3 times 3 times 1 equals 9, and the sum again is 15. So 15 on both sides is the same, therefore the function d of a is a three-linear function. Okay, that was all about n-linearity in this video. I think that the book Hoffman and Kunze has given it slightly difficult for a first-time reader, and I hope that the examples I gave was somewhat helpful. Thank you very much for watching.